Hello friends, good morning. Welcome to our channel. In previous videos, we have to discuss the definitions of homomorphisms and some results based on homomorphism. In today's video, we will discuss some more results on homomorphism which are very important in the group theory. Theorem: let phi be a homomorphism of a group G onto G dash with kernel K. Let X belongs to G such that phi of X is equal to X dash belongs to G dash. Then show that K of X is equal to phi inverse X dash. It is given in the theorem that G and G dash are in two groups. Phi is homomorphism from G onto G dash and K be the kernel of the homomorphism phi. We have to prove that K into X is equal to phi inverse X dash, where X dash belongs to G dash and X dash is the image of X under phi. Proof: let G and G dash are any two groups let phi G to G dash be a homomorphism K is the kernel of phi. This implies K is equal to X belongs to G such that phi of X is equal to identity of G dash. We know that kernel of phi is always normal subgroup of G. This implies Kx is the right coset of K in G as X is belongs to G. We have to prove that Kx is equal to phi inverse X dash. As X is belongs to G, this implies phi of X belongs to G dash. Let phi of X is equal to X dash belongs to G dash. Suppose y is belongs to k into x. This implies y is equal to k into x for some k is belongs to capital K. Now phi of y is equal to phi of k into x is equal to phi of k into phi of x, because phi is homomorphism, which is equal to e dash into phi of x. E dash is the identity element of g dash, which is equal to phi of x is equal to x dash. Thus phi of y is equal to x dash is belongs to g dash. This implies y is equal to phi inverse x dash, but y is an arbitrary element of kx. This implies kx is contained in phi inverse x dash. Put it equation number 1. Again we assume z is belongs to phi inverse x dash. This implies phi of z is equal to x dash. Phi of z x inverse is equal to phi of z into phi of x inverse, which is equal to phi of z into phi of x, its whole inverse, is equal to x dash into x dash inverse, because phi of z is equal to x dash, which is equal to e dash. This implies z x inverse is belongs to kernel of phi is equal to k. This implies z x inverse belongs to k. This implies z x inverse into x is belongs to k into x. This implies z is belongs to kx, but z is an arbitrary element of phi inverse x dash. This implies phi inverse x dash is contained in kx. Put it equation number 2. Now from equation 1 and 2, we have kx is equal to phi inverse X dash, which is the required result. Next theorem, a subgroup N of the group G is normal if and only if it is the kernel of some homomorphism. In this theorem, we have to prove that if N is a subgroup of any group, normal subgroup of any group G, then it must be the kernel of some homomorphism. And if group G has a kernel N, then it must be normal. Proof. Let G be any group and N is subgroup of G. We assume that N is normal subgroup of G. We have to prove that N is equal to kernel of some homomorphism. As N is normal subgroup of G, then G by N is the quotient group let we denote it by G dash, that is G by N is equal to G dash. We define a mapping phi from G to G by N, defined as phi of x is equal to nx. We prove that phi is well defined. Let x y belongs to G such that x is equal to y, then nx is equal to ny. This implies phi of x is equal to phi of y. So phi is well defined. Now we have to prove that phi is homomorphism. Phi of x into y is equal to n of x into y, which is equal to nx into ny, which is equal to phi x into phi y. Therefore, phi is homomorphism. Now we find kernel of phi. Kernel of phi is equal to x belongs to G such that phi of x is equal to identity of G dash is equal to x belongs to G such that phi of x is equal to identity of G by n, which is equal to x belongs to G such that phi of x is equal to n, because n is the identity of G by n. This is equal to x belongs to G such that n of x is equal to n, which is equal to x belongs to G such that x is belongs to n, which is equal to n. This implies kernel of phi is equal to n. Hence, if n is normal subgroup of G, then n becomes the kernel of phi where phi is homomorphism mapping. Conversely, suppose n is the kernel of some homomorphism, we have to prove that n is normal subgroup of G. Let x is belongs to G and n is belongs to capital N is equal to kernel of phi. This implies phi of n is equal to E dash. E dash is the identity of G dash, which is equal to n. Now, phi of x n x inverse is equal to phi of x into phi of n into phi of x inverse, which is equal to phi of x into e dash into phi of x whole inverse, which is equal to phi of x into phi of x whole inverse, which is equal to e dash. This implies x and x inverse is belongs to kernel of phi is equal to n. This implies n becomes the normal subgroup of G. So in the next video we will discuss some results based on isomorphism. So keep in touch, watch our videos and subscribe our channel for more and more videos on abstract algebra. Thanks to all. Have a nice day. Bye bye.